This is the fourth part of probability video. Now we are going to do probability distribution function, different probability distributions. The three types of distributions we are going to deal here are binomial, Poisson, and normal. In this case, binomial and Poisson are they use discrete random variable. They are they are data from discrete random variable, while normal is from continuous random variable. Let's first start with binomial distribution. This is a discrete distribution, as I have just mentioned. There are some properties with which you can actually identify if the data given follows the binomial distribution or not. The first thing is it is discrete, and the second thing is you will be having the events being repeated in such questions. That is, the events, or here we call them as trials. You'll have repeated trials. That is, if you toss a coin, you'll be repeatedly tossing it for maybe 10 times or 15 times or something like that. So the trials are repeated, and each trial has only two outcomes, which are here success or failure, and you don't have any other outcomes from each trial. And the probability of success for each trial should be the same, as well as the probability of failure should also be the same. If the probability of success is 1 over 3 for the first trial, it should be 1 over 3, 1 over 3 for every trial that you have been uh, doing. And in that case, probability of failure would be 2 over 3, because the probability of success plus failure should be giving you a total of 1. So if I call probability of success as P and probability of failure as Q, small p and Q, then P plus Q should be equal to 1. I can also write Q, which is probability of failure, to be equal to 1 minus probability of success. The next property that you should note in questions under binomial distribution is each trial is independent of the previous one. That means if you toss a coin second time, it is not going to depend on the trial which is done previously, that is the first time. If you the trial, the outcome of the second trial does not depend on the outcome of the first trial. Okay, this we have already done. Dependency can come in questions like not replacing the marbles inside the box. So such questions cannot be considered for binomial distribution. Each trial is independent of the previous one. Now let's go for an example. You can have like tossing a coin many times. Say I'm tossing it for 10 times, and the outcomes here are, we usually say head or tail, but if I say getting ahead is one outcome, the second outcome would be not getting ahead, that is the failure. If getting ahead is a success, then not getting ahead is a failure. Whether you are getting a tail or not is not our botheration. It is getting ahead or not getting ahead. So if this is P, probability of getting ahead is P, which is half here, then Q is also equal to half. You'll understand this better with rolling a die. I roll a die for again 10 times, and the outcomes are, if I want my random variable to be getting a 4, then the outcome would be getting a 4 or not getting a 4. Okay, we don't bother about getting a 5 or a 6 or 1 or 2, but it's just getting a 4 or not getting a 4. So getting a 4 probability is 1 over 6, and not getting a 4 is 5 over 6. And this is all that we want for binomial distribution. So the notation for binomial distribution would be a random variable x follows a binomial distribution with n trials and p as probability of success. In the above case, x was following for tossing a coin 10 trials with the probability of success as half. The second case for rolling a die we did for n was equal to 10 times, and the probability of success was 1 over 6 because getting a 4 was considered to be the success in this case. And the formula for a binomial distribution is ncx p to the power of x q to the power of n minus x. You can also write this as ncx p to the power of x 1 minus p to the power of n minus x, and this is probability of the random variable taking the value x. And as we have told, this is a discrete distribution, therefore the values of x are discrete and they take values like 0 1 2 3 etc. Also, since p is a probability, it is between 0 and 1. Let's consider an example here. Say I have a random variable which follows a binomial distribution with 10 trials and 0.2 as its probability of success. Then what is the probability of x having a value of x, which is here it is 10cx, 0.2 to the power of x, and 0.8 to the power of 10 minus x. Here n is 10, therefore 10 minus x. So you can easily find out what is the probability of x is equal to 4. You just substitute 10c4, 0.2 to the power of 4, and 0.8 to the power of 10 minus 4. You can get the values from the GDC. Using GDC, you don't have to expand all these things. You can just use the function binomial PDF, binom PDF of the number of trials, the probability of success, and the number that you want your random variable to be. So once you plug this into your graphing calculator, you will get the answer for this binomial distribution. If I have a question like what is the probability of x being less than or equal to 4, then you need to use your binom CDF, cumulative distribution function, and all the other things are the same. If I want to find the probability of x being greater than or equal to 4, this should be 1 minus p of x less than 4, because the CDF cumulative gives the values from 0 to the particular value x. So for values more than x, you need to subtract this from the total, which is 1. So 1 from the x will give you greater than or equal to x. Okay, less than or equal to x will give you the value of x greater than or equal to x. Therefore, for any problems in any of these probability distribution, when you have random variable being greater than a certain value, you cannot directly use the formula binom CDF. You need to subtract this 1 minus p of x less than or equal to the number given. Not equal to, it is less than because equal to comes here. In this case, it is discrete. I told you the value less than 4 would be 3. Therefore, less than or equal to 3 should be done here, because the value is included in the CDF. Okay, so if you have less than sign and if you put a 4 here, it doesn't give you less than 4. It gives you less than, or it has to be 10, 0.2 and 3 in order to get the value of px less than 4. If you substitute the value 4 here, then you are getting px less than or equal to 4. Okay, remember this. You have to change the number to equal to sign with the inequality. So this is 1 minus binomial. I just said binomial of CDF 10, 0.2, 3, and you can easily get the values from the calculator. What if you want x less than or equal to, or x greater than or equal to 1? If it was not 4 or it is just 1, we know that x starts from 0 1 2 3, right? We just gave this formula a little while back. This would be, as I defined in this case, would be 1 minus p of x less than 1, not equal to 1. So the value of x less than 1 would be just 0. So instead of doing less than or equal to 0, I need to put it equal to 0, because there are no values less than or equal to 0 for this distribution. Therefore, this is the way you have to do. If you have binomial with x greater than or equal to 1, you need to change this to 1 minus px equal to 0. And this becomes 1 minus binomial PDF, there is no CDF here because it is equal to 0. PDF of 10, 0.2 and 0. So x less than 1 becomes less than or equal to, sorry, equal to 0, and it cannot be written as, this is wrong. You cannot have values less than 0 for x. Now let's move on to expected value and variance of x for binomial distribution. Extended expected value for x would be NP, and we know that the notation for expected value of x is mu, and variance of x is NPQ. You know what are the notations NPQ are. The standard deviation therefore would be root of NPQ, n times p times q. Let's do an example now. Contains 7 marbles, of which 2 are blue. A marble is selected, its color noted and replaced. So this is, you can see that the event is independent, the trial is independent there because it's been replaced. Now the next sentence here would be, this process is repeated 50 times. And this is where you actually identify this as binomial distribution. So there is a trial which has been repeated. So the question is, find the mean of the number of marbles selected and the standard deviation of the number of marbles selected. So we know that mean is equal to NP and standard deviation is NPQ with a root inside. So the N is 550 here, and P is selecting a blue marble where you have 2 blue marbles out of total 7 marbles. So it is 2 over 7. Therefore Q would be 5 over 7. It's easy to substitute here. NP would be 50 times 2 over 7, and this would be square root of 50 times 2 over 7 times 5 over 7, and you can simplify and get the answer for that. So this is all about binomial distribution. Let's move on to Poisson distribution. I told you before that Poisson distribution is also a discrete distribution. Therefore the random variable is discrete here, and there is a certain way in which the questions will be framed, or in which the situation would be considered for Poisson distribution. In these there are some examples which are coming up now. Looking at these examples, you will understand what exactly is a Poisson distribution. These are some of the examples that you could notice in questions on Poisson distribution. You could have noticed here that every question has a number of something per something, right? Number of accidents per day, number of flaws per square meter, number of bacteria per liter, cars per hour, children born per day. Okay, that is something over an interval of time or area. This is over an interval of time. This is over an interval of area, over an interval of volume, or this is again time and time. So the event occurs, the number of outcomes over an interval. It is always seen in questions on interval, sorry. It's always seen in under the question on Poisson distribution. So whenever you see something like number of something per something, then you can identify this as Poisson distribution. In more properties on this, the number of occurrence, we said this number of some occurrence per interval, per some interval, right, of time or volume or whatever. This has to be the same for every time, in every time the event occurs. Like number of children born per day does not change from one day to another. So every day the number is going to be the same. This is the average number of children born per day in a hospital or something. So the number of occurrence per interval which is given is the same throughout. It doesn't change from one interval to the other. And again, the events are independent. Like if you have number of children born on one day, it doesn't depend on how many children were born the previous day. So the events are independent. The number of event occurring over an interval occurs uniformly. That is, if it occurs for one day, if there are five children born on a day, then there would be 10 children born on 2 days. So you can say if you have an average of 5 per day, then the average for 2 days would be 10. So it's the same, you don't change the number there. So these are certain properties that you would like to look into if you want to decide whether the question is Poisson or not. And this is a very major idea which you can immediately identify as Poisson distribution. The notation for Poisson is a random variable x follows Poisson, and the parameter we are using here is mu, which is the mean. Okay, so in this case 5 would be the mean, 5, p of 5. Poisson is capital P of 5. So mu is the occurrence per interval that is given for the given number of intervals. If you are considering for 2 days, then x would follow the random variable of 10, because you have to multiply the average by 2. So the number mu, parameter mu, depends on what interval you are dealing with in the question. And the formula for the probability when it follows the Poisson distribution is e to the power of minus mu. Mu is what I just told about, the parameter, mu to the power of x over x factorial, and this is discrete, therefore the values of x would be 0, 1, 2, 3, etc. If we say that there are 5 children born per day, and if your question is asking for probability of having 2 children born on 2 days, right? What is the probability that x is equal to 2 when we are considering 2 days? So in this case, mu would be, as I just told, 10, and then your formula would be p of x is equal to 2 would be e power minus 10, 10 to the power of 2 divided by 2 factorial. Same properties apply for those which are with less than or equal to, and for greater than or equal to. Okay, for less than or equal to, you can use Poisson CDF directly, and what you are supposed to enter in your calculator is the value of mu and the x that is given in the question. For p of x equal to x, you can use Poisson PDF because it's equal to, so it's Poisson PDF mu comma x. This is how you have to enter in your calculator. For, as usual, for x greater than or equal to x, you need to consider this as x less than x, and again you need to consider this as one number less than that, so 1 minus p of x less than or equal to x minus 1. For example, if you are getting confused with this, let me use the same example. X greater than or equal to 4 would be 1 minus p of x less than or equal to 3, and you need to find 1 minus Poisson CDF, because less than or equal to is always CDF of mu is whatever mu is given, and it is 3. Important thing to note here is the question would have a rate, say it has a lambda per unit time or whatever time it is given, and your question would be to find for some unit of time, say t. In that case, mu would be equal to lambda times t. This you should not forget. Okay, if you have say 1.5 accidents per day, or per day, and you are asked to find the number of the probability of the accidents being 5 accidents per in 5 days. So you cannot just take 1.5 as mu. The mu would be 1.5 times 5, and this is very, very important. If you miss this, your whole question, the marks are lost. So we can have a typical question like this. Say if the given rate of growth of bacteria is 1.2 per every 6 hours. Okay, it's not unit now, every 6 hours. Then find the probability that at least 25 bacteria, that is, there is a growth of at least 25 bacteria in one day. So at least 25 bacteria in one day. Remember, the question was given as 1.2 per 6 hours. The question asked is for one day, and there is a word at least. At least is greater than or equal to 25 in one day. Therefore, the mu should be immediately changed. Mu is 1.2 over 6 times 60. So the mu should be 12 here. Therefore, this would be 1 minus, again you can't directly do the question for greater than, so you need to change the question as less than 25, which would become less than or equal to 24, and which would be this in into the GDC, you can get the answer directly. And in Poisson distribution, both mean and variance are equal to the value of mu. The properties here, the conditions for the approximation, when mu is very small, that is mu in the sense it is p for binomial, and when the number of trials is really huge, very huge. Okay, so if a random variable follows a binomial distribution of p, b and p, then if p is very small and n is very large, then this can be actually changed to like this, where mu is np. It will have just two options for outcomes. There will be no rate of any occurrence over an interval. So the question would be actually given like a binomial question, binomial distribution question. You will not see anything like number of occurrence per hour or per day or something like that, which will tell you it is a Poisson, but you will not have them. Instead, you will have a question as if it's a binomial question, but the trials should be really huge and the probability would be really small. In such cases, you can think about going for Poisson distribution. Say usually the p, when it is less than 0.05, or when n is somewhere greater than 20, not exactly, but something greater than 20, and the p when it is less than 0.05, then you can actually change binomial to Poisson distribution. So you will have all those things like a binomial, you'll have a trials repeated, you'll have n, you'll have p, but you'll not have the number of occurrences per interval. So once you see that the number of trials is really huge, then think about using Poisson in that case. Okay, here is an example question for you. In a box of certain tools, 4% are observed to be defective. So in one box, 4% is observed to be defective. If a set of 40 boxes are considered, what is the probability that the set contains at least one defective tool? What is the probability that the set contains at least one defective tool? It doesn't look like anything of Poisson distribution because there is no rate, but 4% is the probability of defective tool, right, which is equal to 0.04. So you can see that the p is really small. You can take this as p, and the trial, the moment you saw 40 boxes, then the trial is 40. Therefore, you can actually use Poisson distribution here, where mu is equal to 40 times 0.04, which would be 1.6. So using 1.6 as your mu, you can actually do this as Poisson distribution. So which would be e power minus 1.6, 1.6 to the power of x divided by x factorial. Now the question is at least 1, that means is greater than or equal to 1, which is 1 minus p of x is equal to 0, as we have done before, which is 1 minus e to the power of minus 1.6, 1.6 to the power of 0 divided by 0 factorial, which would be 1 minus e to the power of negative 1.6. So this is how we are supposed to change a binomial distribution to a Poisson distribution. So we have done all the things about binomial and Poisson distribution. In the next video, we'll do about normal distribution.